And we're very happy to have Anton Mellit from Vienna, who tells us about the AQT algebras and Topological conjecture.
Okay, thank you. Yeah, so I want, maybe let's start with something simple. I'll talk about this AQT algebra. But first, some general remarks. That I want to advocate the idea that linear recursions are much better in possibly several variables, several indices are better than nonlinear. So so for example, let's consider the set of Dick paths. So what is a Dick path? So you fix n, and you consider this is kind of staircase path. So there is a diagonal here. There's a case n equals 5. This point is n, and then I go up or right or up or like this. And it is well known that number of Dick paths is the Catalan number 1 over n plus 1 to n choose n. And there is a beautiful recursion that has positive coefficients satisfied by Catalan numbers. It is Cn plus 1 equals sum of i's from 0 to n, Ci, C, n minus I. And the proof goes by, like, how do we prove this? We look at the first point where the path touches. So maybe I made a mistake in the formula. I don't quite. So the first point where the path touches, this picture like this. So, and let's suppose this distance, maybe I is from 1. Okay. This distance is I, and this distance is n plus 1 minus I. And then what we do, so here in this area, so this is my diagonal. Maybe it's better to move it a little bit. This is diagonal. This is the beginning point. This is the end. And then here, in this area, path does not touch. So what we can do, we can move it down a little bit. So we move this part down. So for instance, if you had something like this is the first touch point, it means that the path must stay somehow like this. And then we can move it down and we get a shorter path. Okay, so that's how you get this. So now you have to enumerate over paths of length I minus 1 and the path of length n plus 1 minus I. So we get 2 paths. length I minus 1 and n plus 1 minus I. That's the basic idea if you have to fix the so the first few Catalan numbers are given as follows. So we have n, Cn. Let's see, we start beginning with 1. There is 1 pass. Then length 2, we have 2 pass corresponding to this and this. And then for n equals 3, we have 5 of them. And drawing like this. Or we can go like this, or we can go like this, or we can go like this, or we can go like this. And then when n is 4, then we have 14. Okay, that's so. But here is one other recursion that is linear. So another recursion. But it depends on 2 indices. Let's count. So we let's count C and K is the number of paths from 0K to n. So we start at height k. We have here height k, and then the diagonal, and then we count paths which end at this point. Okay. Then it is trivial to write a recursion because to get to this point, we can come it from above or from the right. So you get C and K equals, what is it? Either you come from above, so you get n k plus 1, or you come from the right, and that means from C n minus 1, k minus 1. Okay. So now we have different generalizations of Catalan numbers, and let's see how it works. So generalizations of Catalans is when you count dig paths, but you count them with some weight, and one of them is like this. You count dig paths of length n, but put t to the area. So what is the area?
Yeah. I'm sorry, Anton, if k is equal to 0, then you cannot come from the right.
Yeah, that's a special case. Yes, you get Cn0 equals Cn1. So area is the number of complete boxes, grid boxes between the path and the diagonal. And so what do we get? We get something like this. You get, for instance, n equals 2. Okay, let's again draw the table. And Cn of t. When n equals 2, we have 2 paths. One has 1 square, another has no squares. So we get 1 plus t. For 3, we have t cube. So that's the largest one. Then there is one like this. So again, we can have this kind of recursion very easily extends to this case. So we obtain, I don't know, C and K. So C and K will denote the similar kind of summation over a subset. And there will be like C and K plus 1. Either we came from above or we came from the right. So we get T to the 1, K minus 1, C n minus 1, K minus 1. Okay, so you can produce this kind of recursions easily. And let me write one particular recursion. Maybe that's interesting. So, so a modified version of this we go from NN to K to 0K, but the last step must be horizontal. Then everything is frozen. Is it? Yeah. Then you get that C for this version C and K of T. So you just need to count this last step, which is T to the K minus 1, and then you could come from K minus 1 plus and so on, an increasing sequence of indices. And here is another version, which is really cool. So another condition, another counting, is when you C and K are similar, so sum over paths which touch the diagonal in K points. Then let's see. But then you want to count so-called DINF statistic. I don't want to define it, but the point is that you get the same kind of counting, T to the K minus 1 times C n minus 1 K minus 1 and so on. So similar formula. Okay, so you can write this kind of recursions, and then maybe it can lead you to the definition of Qt Catalan numbers. So there is a new Qt Catalans look as follows. So it's again a similar kind of enumeration, and I wanted to compare the T Catalans and Qts. That's why I showed them both. So for 2 you get Q plus T, and for 3 you get Q plus Q squared T plus Qt squared plus TQ plus Qt. So the Qt Catalans obtained by counting both the DINF statistic and the area statistic. So this is from Garcia, Bergeron, Haiman, Haglund, so on. And this is, you have some statistic where you get 2t to the area and q to the diff. So very interesting thing. There turns out to be symmetric in respect to q and t, which is somewhat mysterious. And this is how the shuffle conjectures begin. So on one side you have this counting of dig paths, for which you can write recursions, and then here is another side. So I need modified McDonald polynomials. So these are some polynomials in variables q, x, q, and t, where x stands for the infinite alphabet, and they are symmetric with respect to the axis, so they are inside the ring z, q, t, x, and symmetric with respect to the permutation of the axis. Sorry, can someone unmute the microphone so that I hear at least some noise?
Sure.
I won't
Okay.
promise to mute myself later if gardeners or something start up.
Sure. Okay. So there is modified McDonald polynomials. And once you mention them, there is a whole package of stuff you should mention. So there are so-called McDonald operators. Which are some kind of Q difference operators. And let's denote them by D1, D2, so on. And then once you diagonalize these operators so they act on this QT X, and diagonalizing them produces McDonald polynomials. And so in the end we get that. So there are different versions of McDonald operators, and I want to use the one that okay, let's. So here is what you can do. So I should draw a picture of a partition. So lambda, they're indexed by partitions. For each partition, there is a labeling of cells by monomials. And so on. And then you can consider different elementary symmetric functions on these monomials. And so I can write here EK of this. So these are called weights. You overlay an elementary function in this weight, and that's your multiple. I omit XQT. Okay, and then they together. So there are many properties of McDonald polynomials, but the most importantly it's better to think about everything in terms of the elliptical algebra. So let me draw the picture of the elliptical algebra. So I am drawing these McDonald operators. And then I draw here the some other operators where, so di I already mentioned, but fi's are operators of multiplication. By certain generating set of symmetric functions, which and you can do different versions with splitisms and then obtain something simpler here, but then something more difficult appears on the other side. So, okay, so you have these two different kind of operators. Let's say we have two kinds of algebras acting on symmetric functions. One algebra is just multiplies by some symmetric functions. So this algebra is just obtained by multiplication. So multiplication algebra. And then it's obviously a commutative algebra. And then there is this other algebra generated by the McDonald operators. And this is algebra of diagonal operators. In this basis, in the H lambda basis. Okay. And then once you try to understand relations between them, something very complicated happens. So in principle, you can write down generators and relations, and Schiffman and Vassereau did it. And but it is impossible to compute with this presentation, so it's very, very complicated. Okay, and what is the shuffle conjectures? So shuffle conjecture usually has two sides. On one side, you write things like, so I didn't say it was Nabla, but so Nabla of applied to Hn is just a product of weights times Hn. Okay, so what does the shuffle conjecture say? It tells you the formula for this expression, where En is just the elementary.
Oh, we want H lambda instead of Hn.
H lambda, sorry. Yeah. And then it tells you that this expression is a sum over dict path. And then maybe I should. So again, I don't want to be too. So you put here T to the area, and then some kind of LLT polynomial associated to the dict path.
Sorry, and what is Nabla again?
What here is Nabla? It's
okay. Okay. Mm-hmm.
Yeah.
So this is the definition, right?
Yes, yes. Yeah, so this is one of the things you can plug into this machinery with elliptical algebra, and that's what.
Sorry, what is LLT?
Right. So the point is that these Qt Catalan numbers that I introduced in the beginning, they have some sort of generalization, which is not even a Qt function. It is a, sorry, it's not even Q function. Well, T to the area stays the same, but then there was Q to the dinf. And now this Q to the dinf becomes some symmetric function. So, and
I'm sorry, I guess I'm still a little confused. Can you expand a little? So when we write product of weight,
yeah.
So it would be like the kth elementary symmetric function if lambda has k boxes.
oh, I see.
Yes.
And it's possible to express this nabla in terms of Magellan operators?
Well, it is sort of in those operators, in terms of those operators that I mentioned, these, it's just dn. But usually people use other Magellan operators.
Thank you.
Okay, and so now I will talk about. So you see that there is something kind of combinatorial on the right hand side, which is enumeration over dict paths, and then you do some combinatorics with the dict paths, and there is nabla, this whatever it is, some evaluation of something in the elliptical algebra on the left hand side. So this is general shape of the general idea of shuffle conjectures. Okay, now let me introduce the AQT
Sorry,
algebra.
Anton, is there a conjecture when you replace En by an arbitrary short polynomial in terms of dict path and things like that?
If you replace nabla,
No, En by other short polynomials.
Oh, right. So yeah, so you have to refer you to the Loehr Warrington paper. So there is, instead of enumeration of dict paths, they consider some kind of nested dict paths. And some, yeah.
Okay, thanks.
Okay, so there is also nabla of whole Littlewoods and other things. So now let's talk about AQT algebra and then how does it help us. AQT algebra. And I have to draw a big kind of picture. So I have enough space. So there will be, for each version of algebras, I will have finite version, I have affine, and I have double affine. And let's start drawing, making rows in this table. So finite would be Hecke algebra of Sn. I don't know, how do you prefer to? Then there's affine Hecke algebra. And there is double affine Hecke algebra by Cherenik. So how do you think about the Hecke algebras? You can draw n strands, and you can consider braids. like this. And this is like T2 is this. And then you impose some relations. You impose quadratic relations. Okay. So it's generated by T1, Tn minus 1, model of braid relations and quadratic relations. And the size is roughly like the size of the symmetric group. Now, what is affine Hecke algebra? You now consider braids on the annulus. So you still have some braids. One way to draw the annulus is by allowing the left side, the left wall, identifying the left wall to the right wall. So now you have things like this. And this is a variable I denote y3. So this is generated by y1, yn, and this one's commute. Okay. So what is the size is now polynomials and permutations. Now what about double affine? You can have now the same thing but on the torus. So there is a more precise for precise description. I refer you to Morton Samuelson. There is some puncture, but roughly speaking, now you can have turn in two different directions. So this y's can turn in two directions. Like if you think about the torus, so this on the torus you have two ways, two walls. If you think about the torus as a rectangle, and yeah, that's so I denote the you have y1, yn, and you have z1, zn. And this is crossing one wall, and this is cross another wall. So they're generated by y's, by z's, and again by, sorry, I forgot to write, to put again t's in the case of the affine Hecke algebra. And for the double affine, you have t1. Yeah. So you have two copies of the polynomials and one copy of braid. So think about it. You can cross these walls, or you can just twist around your strands in a normal way. Nothing. So if you want, there are relations, but since there are too many generators, there are also too many relations. So each set of generators interact with another set in a certain way. But interesting is about DAHA is that here you can obtain it by, so T's and Z's form affine Hecke algebra. T's and Y's form also affine Hecke algebra. And there are some braid relations between Z's and Y's. And additionally, there is one single relation which contains T in it. So one relation with T. Okay. So this one's plus some braiding. Okay, so this is a picture of of Hecke algebras, affine Hecke algebra, DAHA, affine. Now,
So, Anton, is there a way to see the spherical subalgebras to see them nicely in terms of pictures?
Yes, I will mention that. Okay. So this is one piece of way of. Now let me just. So one more piece of insight is the line category and its Q deformation and let's say home free category. So this gives you a way to think about for instance, the Hecke algebra. So what is the Hecke algebra from this point of view? So well, the idea is that to look at the category of representations of UQ GLN where we don't know n. Maybe n is too large, and then we still want to do something in this category, and sorry, n. I have to use a different letter because and this way you get so this category must contain standard representation. So there is this standard representation, standard rep V, and we have its tensor powers, V tensor V tensor V tensor V. And then we have, this is a braided category, so we have braidings, and then we get Hecke n as just endomorphisms of V tensor itself n times, and somehow that's all. So you have this artificial category where you can have one object and its tensor powers, and since you know all the endomorphisms, so this is a way to think about Hecke algebra from the point of view of not knowing what is capital N. And now let's do this AQT. So what is this AQT? So let's consider a category. So consider the category UQ JLN rep. But then let's consider also there some distinguished object. Let's call it S, which is the symmetric m's power of the standard representation. And let's continue playing our game. Game where we don't know where we don't know both and so what kind of extra structure we get? So again, we can form some tensor products. So we can write S tensor V tensor V. This is so we have objects like this where we can put KVs. But you see, in the Hecke algebra, there was in the sequence of Hecke algebras, there was no way to change K. And now we have a way to change K because we have, well, how do you put it? So there is this SM, which you don't know, but there are morphisms from SM to Sm-1 tensor V. And then, vice versa. So we obtain, if we denote these objects by Vk, then we obtain morphisms from Vk to the first thing gives you a map from Vk to Vk plus 1, which we denote by D plus. And the second map gives you a map from Vk to Vk minus 1. But this dependence on M will be hidden in some parameters. So, and now with this idea, you get the AQT algebra. That's what. So let me again. There are three situations. We have finite, affine, and double affine. And okay, so the AQT finite, and what we are in. So there is an important thing that we want to understand some algebras plus together with some module that well, certain module, and the module in this case in the pictures is given by its home from S. So direct sum, home from S to, well, so everything what you can get out of these operations. M and S. Okay. So in the finite case,
So, and you're taking the direct sum over all K from.
Yeah, over okay, yes.
Okay.
So let's understand this in the finite case first. Finite. Well, it's in finite case, it's not. So the algebra is in general is generated by D plus, D minus, and some T's. And the picture is so the pictures as follows. So we have this S, which we draw and as a thick line, and we have K thin lines denoting V, and then D plus looks like this. and D minus looks like this. And it's clear that D plus increases the number of strands and D minus decreases the number of strands. So this is Ti looks like this. But for instance, the module from S to M minus K tensor V tensor K is one-dimensional. And so the action of the algebra is given by some constants. Why? Because so any home looks like this. So we have thick line, and we have some thin lines coming out of it. If you twist, twisting the thin lines, just multiplies by constant, multiplies by q to the 1/2. Okay, so nothing interesting happens here, but already with affine case, the interesting stuff begins to happen. So affine case, which we denote by AQ algebra, looks as follows. So there are two walls, and so this is some slice of some diagram, a thick line and many thin lines. And of course you can still twist the thin lines. Nothing new here. Then what about y? But so when you talk about y, now there is a you have to specify how it passes around the so we go to the wall and then we reappear from the other side. Okay, and
so it goes under them after it passes the wall, as opposed to like in the other picture, it went under and then over.
No, that was a mistake. Sure, I supposed to do it the other way. Mm-hmm. And then how do I draw D plus? D plus is similar. But for D minus, I want to have a little twist. I kill the last strand.
And also back with your picture of the Ys, you think of it as going under the thick S strand as opposed to like a d plus d minus being absorbed in and spit back out?
So, sorry, I didn't understand.
So for the YI picture,
Yes.
the way that the strand interacts with the thick S
Right.
strand, and you can think of it as going under it, like it goes under the other strands, but you could maybe think of it as being like absorbed into it and then spit back out, like from a D plus D minus.
So the commutator involves some scaling relation and this something like this. Or maybe inverses. Now I'm not able to make a precise formula here. Okay, that's okay. But already here with this picture, you can draw another. So you have a disk path. If you have a disk path, then you can visualize it as so you have some disk path, you get some, looks like this. So we start from the topmost point, and we go downwards, and we replace every this step by d plus, and this one by d minus. Then, well, you see here that this is already, when I in the beginning spoke about recursions, this was the most natural recursions for disk paths were the linear recursions involved two coordinates, and we had step from the right or step from the top, and it turned out that this gives some pictures without intersections. Yes. So, for instance, this becomes, I have some sixth strand, then one thing comes out, then one more thing comes out, and then this thing comes and dies here. So the thickness here is n. Then if this is n, then, sorry, m. And then it becomes m minus 1, m minus 2. But then this guy dies. And then a new one comes out. And then they both get parked in this. So you can see that it gives you, you should think about it as a form in the annulus without intersections. And so this gives you the LLT polynomials corresponding to disk paths.
Excuse me, what does LLT stay for again?
Sorry, just momentarily.
Leskulik Vertibon.
Oh, I see.
Okay.
What do you mean exactly by it gives you LLT polynomials?
you see that when I have M here, I get a spherical affine Hecke algebra. So elements of the spherical affine Hecke algebra are like you take symmetrizer and then you put element of affine Hecke algebra and take another symmetrizer. And here I computed the so on one side, this picture can be evaluated in spherical affine Hecke algebra and gives you symmetric function.
Okay.
On the other side, I get an LT polynomial. So this is a way to compute those symmetric functions. Because and what is AQT from this point of view? So we have to do the same on the torus. So we have now there's this, but one way to think about it that there is, so strands can cross two kinds of walls. One, the old ones, and the other one is, you should imagine a wall in front of you and on the other side of the blackboard. And so for fixed K, we have generators T1, Tk minus 1, Y1, Yk, and Z1, Zk. And there are D plus, D minus, which change K. And then, so there are certain relations. And the relations are so that Ti's and Yi's give you this AQ algebra. Ti's and Zi's form another AQ algebra. And the connection between them are given in some simple relation like Y1 D plus star is T times Z1. Oh, sorry, yeah, I didn't say what's T plus star. So there are also on the rectangular presentation of the torus, there is two ways to create something, and I should take one way to kill something. So this is a thick strand, and okay, so now.
Sorry, can you explain once again how you draw the thick strand on a torus?
See, everything lives on the torus times unit interval.
And the thick strand lives on the point times the interval.
Yes, exactly. Yeah. Okay. So I have to, over time I should kind of make some kind of punchline. So how is it useful for proving shuffle conjectures? Conjectures is that so the idea is that it turns out that nabla should be not sort of as an operator. It is an automorphism of the algebra. So is an automorphism of the algebra corresponding to the then twist. And then once you have this idea, then you kind of very quickly to just so how to define it on AQT. You simply replace, so why you keep for, so it depends which then twist you have to pick. So Z1 goes to Z1. You fix one set of variables. Sorry. Like this, but then you y1 gets multiplied by z1 y1, and then you have to compute how the other operators, other variables like other operators like, and or d plus goes to z1 plus. So to define then twist, it's very easy to define it on it's very easy local rules in terms on the operators, and then very easy to check relations. And so you get this well-defined operators. You prove that it is well-defined. And then yeah, so this is.
And then my topology isn't good. So for the Dane twist, is that like if you're thinking of the SL2 action, you're doing like the 1, 1, 0, 1 matrix?
Right, yeah. So if before Z1 was like this, then afterwards, for instance, just one strand, then afterwards it looks like this. And this is a product of Z and Y. Okay. So it's easy to check relations, and then easy to check the recursions in the, and also recursions for DIC-pass. And what else? So so basically, yeah. So the shuffle conjectures are proven just by verifying certain recursions using relations. And then there is this delta conjectures. For in my notations in this notes for k of En, where k is between 1 and n. So you remember, if you remember, D was a diagonal operator, and you're supposed to evaluate elementary symmetric functions in the weights. So there is this delta conjectures for decay by Haglund and Wilson. And after some discussions with, so that Delio computed recursions, and his collaborators computed recursions. And it turns out that there are more actions on AQT algebra, where for any f function of z of one variable, you can define d plus to send it to f of z1 times d plus. And f of u linear gives delta conjecture. But you see that there exists an action of much bigger algebra, because you can put arbitrary series. And now the question for you is, for Olivier. Do you see the section of a big algebra on the elliptical algebra? So the elliptical algebra is just when you start with 0 strands and end with 0 strands. So begin at k equals 0, apply some operators. And then end at k equals 0. This kind of expressions belong to the elliptical algebra. And so we get an action on the elliptical algebra. And all this also occurs on the Hilbert scheme with Carlsson and Gorski. We have Nakajima operators. It turns out that this is just D plus and this is just D minus. So the operator is given usually as a kind of picture, like going up and down, become just the product of operators in the algebra. So more generally, you D plus, then you apply Z1, so you rotate several times, and then apply D minus to go down. So that's for Nakajima operators. That's it.
Okay, let's thank Anton for the talk. Well, please, if anyone has questions, please ask.
Maybe one vague question. Can you play this game to define this AQT algebra, not with the symmetric power, but with the exterior power of the fundamental representation, of the standard representation? What kind of algebra would you get?
The thing is that if the interchange Q and minus Q inverse exchanges those.
Okay, so it gets the same algebra, essentially.
Yeah, you are free to choose either you want to play with exterior or
Is there any relation between these AQT algebras and KLR algebras? Because the diagrams, or Quiver-Schur algebras, the diagrams look very, very vaguely with these merge and split operators.
KLRs are some degenerations, right? They are.
KLR are, you can view them as, they have some cyclotomic quotient of Hecke algebras, type A.
Well, so I don't know. I haven't looked at KLR.
Okay, I mean, it's just very superficially. Same kind of pictures, a little bit.
When you said more action, did you mean something like a whole SL2Z or some extension of SL2Z?
It's like some kind of deformation, maybe like a Lie algebra action. So you have SL2Z, but additionally some infinitesimal action given by, you see the, you have a sequence of generators, because you are allowed to put here arbitrary function of one variable. So you can think about it like like a Lie algebra with Lie algebra action with infinite sequence of commuting generators.
Is there action of whole, no, honest SL2Z, not Lie algebraic?
Oh, and honest. So in this business, when people say SL2Z, it's
maybe braid group on 3 threads.
Usually it's an action of some monoid, positive part of SL2Z.
Mm.
And there is a way to, so if you allow negative negative powers of y's and z's, then there should be an action of some kind of cover of SL2Z, because it's not quite SL2Z, because when you go around the puncture, things get twisted, right? When you have D plus, for instance, you need to choose which way you are splitting out.
Thank you.
Can you spell out relations between AQT and DAHA or spherical DAHA in some more details?
So, okay. So from what I was saying, maybe. So DAHA with index m controls just m strands, and then you can multiply by projectors corresponding to strands labeled m, 1 to m, and on the left by 1 up to m minus k. So what does it mean? When you multiply by projector on one side, it means your m strands become one thick strand of thickness m. So you start with this, you do something, and then after you reappear, you get k. So strands simple and m minus k remain here. So this is the module, and the algebra is obtained by taking multiplying by projectors from both sides. Right. And this is you interpolate in M.
And what was the, somehow, maybe a naive question, but what was the role of introducing this AQT versus just DAHA in order to prove the Shuffle conjecture? Why AQT was important?
So in the first part, I mentioned this dig pass and these recursions. So that's these recursions live in a bigger space. So you have dig pass indexed by integer, but you have to go to some to this. You have the C and K. So they correspond now to so dig pass gives you a closed picture where you have this LLT polynomial. You have this web, closed web on the annulus without intersections. But the intermediate steps of the calculation are obtained by slicing it here in the middle. Okay, and so the recursion, you don't have a recursion for the whole picture because the picture is closed. You have to cut it in the middle, and then you have recursions. So in the shuffle conjecture, you have some sums over pictures like this, and you.
I think I'm just confused why somehow. I mean, for all the shuffle conjectures, it's a story about the Dane twist, which you still see just in terms of DAHA without introducing any additional AQT algebra, right? There's apparently some ingredients that you don't see from DAHA without AQT.
So let's draw this picture. So there is this rational shuffle conjecture where you have to deal with torus knots or links. And this is how the picture that you need to compute looks like. And you have this the puncture here. And what you do, you have to analyze what happens if you sort of slide this link parallel and hit the puncture. And the intermediate step would look like so there is this thick strand. So you have some computation where intermediate strands look like this. Sorry. Fortunately, it's too difficult to draw on the so somehow you will have to cut your, so even if you want to compute invariant over a single strand wrapping around the torus, you want to kind of move it, and once it hits the puncture, you cut it into pieces. Mm-hmm. And so intermediate steps of this computation correspond to braids, not just a single strand anymore. So you intermediate steps become closures of pictures like this.
Mm-hmm.
Sorry, I didn't understand your picture. You've got some box at the center of picture.
Yeah, the box has some picture where you also wrap around without something like this.
Okay.
So this is similar to when you have a dig path. And in the beginning, we analyzed our recursion was about how dig path touches the diagonal. And now you move this diagonal up. You can interpret this move as some kind of transformations on the braid on the torus. And yeah. I'm cheating a little bit because I don't have. So let's. I mean, I refer to you to papers like torus, braids, and so one is about Haiman Rozansky homology of torus knots. And another is about toric braids. Yes. Certain pictures that tell you how the recursion looks like, and really it's important to intermediate steps of the recursion correspond to these pictures with k non-zero.
Okay. Any more questions at this point?
Yes, sir. I would
Let's think. So then let's thank Anton.
Yeah, okay, and let me stop the recording.